Good morning, dobre rano, marhaba I dzień dobry. My name is Piotr Chomiuk, and in our morning session, and it's nice to see you again. In this session, we will be talking about mini photoelectric spectrometer and IMPS, IMVS, which stands for intensity modulated photocurrent and photovoltaic spectroscopy. Can you hear me well? Okay. And in today's session, we focus more on equipment, software, sample preparation and mounting, and then we go through some experimental procedures, and of course some summary. So these two setups look the same or almost the same because they consist of mostly. So the light source is the LED revolver that you probably know, or if not yet, so you can come and look closer after the presentation. A potential stat is the circuit for current and voltage measurements, and sample chamber, which is recommended but not obligatory in the mini photoelectric spectrometer setup, but in the case of IMPS, IMVS is obligatory. This is because we measure here alternating signals in wide frequency range, and these two setups are configured in different way. So here we only measure stationary signals, so so the setup is configured to be not sensitive for AC signals, and then we have to take care to screen the sample or just cover with a box to avoid to protect from some external light. But in this case, we need a Faraday cage to screen off some all stray fields and electromagnetic noise and so on. And of course, a cuvette. Our cuvette we just hang on the cage and in the set of electrodes. If we compare mini photoelectric spectrometer with the large, with its older brother, photoelectric spectrometer, the most significant difference is in the light source. So in this case, we have a switchable, compact light source based on 10 LEDs. And in photoelectric spectrometer, there is xenon lamp with monochromator. So if we ever want to upgrade this setup to photoelectric spectrometer, we just save one LED revolver, but we have to invest into whole heavy setup like as a xenon lamp, monochromator, filter wheel, and all these details necessary. The major advantage of the xenon lamp is that we have a continuous spectrum, and we can step by step with some nanometer or less step just scan the full spectrum. And in the case of LED revolver, in this case there are 10 LEDs plus one white, but we have just like this is not a real spectrum. This is something like a, say, pseudo spectrum or comp spectrum. There are only 10 in this configuration, 9 LEDs monochromatic, so even these lines are not equally spaced. But the advantage of the xenon lamp is that it has a large power. This is 150 watts electric power, but this power is mostly used to heat up the cooling water in the cooling water circuit. And after monochromator, we only have some fractions of watts, some milliwatts or so in that range, and it also depends on the slit width. And in the case of LED revolver, we just deliver about 1-3 watts of power exactly to power this narrow line. And of course, the sample chamber is not obligatory, but we recommend it all the times because it significantly increases the quality of measurements. Especially if we measure very low currents, it is much better to protect sample from noise in that Faraday cage. The first activity we have to do after connection, our setup, and before measurements is to perform calibration. And calibration is a process to teach the equipment how much electric power, how much current we have to deliver to the LED to get how much light power. So this is just an LED. We can just zoom in to this field, just near 0. First, for some for very low currents, there is no light. It peels off at a few percent, and the calibration is done this way that from 0 to about 1%, we increase the current with step of 0.1%, and after, when it reaches about 1% of its whole current range, then we increase with 10%. So we can see that there are some very small values, and after that it increases, not necessarily linearly, so this is nonlinear characteristic, so that's why we have to know how much power we need, how much current we have to power the circuit to obtain such a power in milli or microwatts. And the second stage of calibration is when we change the geometry of our measurement, because if we move the sample closer or farther from the light source, there is a cone of light from the LED with a lens we focus. We just how much light of this cone we take in our lens, and then how much light we focus on the sample and how much light reaches our calibrator. And we use a silicon photodiode as the measurement head of our calibrator with area of 1 square centimeter. So the light power which is measured by the photodiode is in microwatts, and at the same time it is we can express it as milli or microwatts per square centimeter. So if we move farther from the light source, we don't have to perform once again all the calibration, which is quite long. We just perform another step, which is geometrical calibration, and only the slope changes. So it is enough if we for each diode perform at, for example, 50%, and then we rescale this curve. And after, when we move farther, the intensity is a little bit less, or closer, it's a little bit more, and then we just rescale this curve by a factor of 0.9, for example, or 1.1 or so. How to mount a sample? So there are several approaches. The most easy way in sample preparation is just if you have a TCO, so ITO or FTO substrate, glass cover, conductive layer covered glass substrate, and we just deposit some anyway from a solution or whatever you want. We deposit some sample on your substrate, and we, instead of this plate, we just put the sample facing the inside. We screw it up. We place two electrodes, reference electrode and counter electrode in this cover. So you can, if you are not familiar yet, I guess, if you are interested, so after the presentation you can come closer and look. And just pour in the electrolyte. For example, a 10% KNO3 solution. But this way is less time consuming and less effort consuming at the stage of sample preparation, because this is just a substrate covered with a sample. And another way is to use two glass plates like this, and there are two glass substrate with ITO or FTO, and between them we place the sample with a spacer, with a insulating spacer, and then we just clamp with a crocodile here and two electrodes here, and the current flows through the sample from one electrode to the other. And now let's switch to PhotoGUI software. Let's get familiar. I guess some of you used previous version of photoelectric GUI, and there are some new features and new philosophy, new way to deliver you the software, because we are changing now from software which is like available for everybody, and if you don't use, if you have your equipment with some modules and don't need other don't have other modules, you don't have all this. Let's switch. And you don't use other functionalities, then it doesn't make sense for you to have all this equipment. Let's go to menu, experiment first. So you can see all the experiments available if you have all of our equipment, but in new way, if you order just IMPS, for example, you will only IMPS and IMVS experiments will be highlighted and available for your setup. And you get a license. License is valid for 1 year, and after 1 year for free you get extension for another year, license for another year, and every year we keep in touch, and then it will be easier for you to keep updated. And okay, let's go to menu devices. First, after connecting up the setup, we click detect devices to find what is connected to our computer, and the computer recognizes that in this on this cable there is controller and potential stat is in one box, and LED revolver is another device, and then we can go, for example, into potential stat, and we have some settings. We can limit, so the voltage or potential range is from -5 to 5 volts, But if you know that you have sensitive samples and you want to avoid a situation that students destroy your sample, you can limit the voltage here. If you know that you are not using more than plus minus 2 volts, you can make it here. Potential ramp is further in the experiment. I'll show you. When we go from one potential to another potential to avoid just a steep step, we can make it slower to apply voltage slowly, not to kick the sample if you know that your sample is sensitive. And we can use or not reference electrode. So in some cases, if you don't like to use the reference electrode, you can turn it off. But it is easier just to short circuit both electrodes, and then we use like two electrodes circuit anyway. For LED revolver, let's click in LED revolver. Okay, this is not connected. There is another, let's get out of this. Let's connect. Okay, and there is button connect. And after the software recognized which devices are connected to computer, we connect it. And now if we go again to menu, devices, and now the software knows which LED revolver, with which wavelengths is connected to our devices. And here is the button to perform calibration, but okay, it is already done, so we don't have to go through it. Okay, and let's escape. Let's go to experiment, and step by step we can focus on some functions. Let's go first to LED manual. Upper, yes. So this is the basic panel to control your LED revolver if you wish not to work connected to other modules. If you just need a light source, so you can select a wavelength, one of 10 LEDs, set the light intensity from 0 to 100%, and another function is use auto close in. So for example, if you need a light source, for example UV for 20 minutes, and you don't have to with your watch control the time, you can just switch on for 20 minutes and go to drink tea or coffee. And for some modulated, so it will be useful in, for example, use ramp is obvious, and modulation is also obvious for some experiments if you need modulated light. But in the case of IMPS, IMVS, you don't have to worry about it because software chooses these options automatically. Next, let's go to experiment. First, let's talk about some samples. And okay, so let's switch to the presentation for the moment. For a moment. The easiest sample to understand, and the first sample that we want to talk about it, just as an introduction, let it be a silicon photodiode, which is just a PN junction, so it is obvious and everybody knows it. If we want to get familiar with a new equipment, first let's check it with a well-known sample, not the other way around, yeah? And without illumination, in dark, there is just an obvious diode IV characteristics. And if we turn on some light, we observe that these characteristics shift downwards, and there are two important points on these curves. And short circuit is the is the current value which is flowing through the circuit when there is no voltage. If we connect both terminals, there is no voltage, there is short circuit, and this current value is so-called short circuit current. Another important value is open circuit potential, OCP, and from the definition it is the voltage value where there is no current flow. So current is 0, the terminals are open, there is no current flow, and this is the voltage value. And if we apply, okay, so let's go to the photo GUI again. So this is for the large photoelectric spectrometer, but it is the easiest way to record our IV curve. So we can define the limits. We start from 0, for example, from minus half volt or so, go to plus half volt with step of 0.11 volts per second. But if we want at once measure the IV curve for different light intensity values, let's go to menu, experiment, and it is IMPS I versus P. We can repeat the procedure for different, here we have, can you scroll in, zoom in? Okay, not so. Potential at this axis, intensity. So, daj mi myszkę. Look, we need some space imagination to imagine that if we cut this graph in slices, for example, let's focus on this line. So this is just for a fixed intensity, for one intensity. If we look at it, it looks like an IV curve. If we connect these points, we have this in that quarter. Let's go back to the presentation. Maybe not. It will be easier this way. This is our IV curve. So, fotoguj poproszę. So, as you can see, if you connect in your imagination these points, they reflect this situation, this IV curve in this condition. And if we can increase the light power, we can imagine that if we connect these lines, this is something between, and at the maximum light power. Yeah? Can you see this? Okay. So in this experiment, we can define the voltage range, step, and on the other axis, light intensity. So the more steps, the narrower steps we do, there are more points, so this graph, this 3D graph, looks more continuous, and it will be easier to imagine. Okay, let's switch to the presentation. Another experiment is open circuit potential versus power. So this was the dark current, and if we switch on the light for some value of light intensity, we can observe another IV curve with OCP value that is shifting along this axis. If we increase more light intensity, we have another curve and another. And if we imagine that we introduce another dimension, light power, and we connect these points, we have an OCP versus light power graph. Let's switch. And we go in many experiment. OCP versus OCP, one more up from the dot. Okay. So again, we can select for which wavelength we perform this experiment, because for different wavelengths, the OCP, the sensitivity may be different of our sample. We define the range from initial light power from, say, 0 microwatts up to, for this LED, for this wavelength, the maximum available power is 4,500, so 4.5 milliwatts with the step. The denser step, so this profile is better, is more fluent. And of course, let's go to another tab. We have two tabs, so we can observe the experiment live, how it goes, how it is measured, and the result. Let's switch to the time tab. Let's focus, look. We can, yes. We can zoom in. And what the program does, we also can define some time slots, time windows, and we give 5 seconds to the circuit to get stabilized after we start the experiment. It may be 5 seconds. We can give 10 seconds to get stable if the sample is charged before we can increase some time to let the sample discharge. Shutter open, shutter. There is no mechanical shutter like in the case of the large photoelectric spectrometer. We control it just electrically. We don't have to use a mechanical shutter. But it is like this is just a name for this feature. We open shutter for 4 seconds, then we close shutter for 2 seconds. Here we see 4 seconds and 2 seconds, and we measure the difference. This value minus this value gives us the point. Let's switch to the other tab. Gives us this value for 20 microwatts, and so on. These times, let's go to many devices. Second tab, photocurrent calculation. Use last 50% and skip last. If we work with a fast sample, like a silicon photodiode, the response when we switch on the light the response is fast. It's almost rectangular or so. But if we work with a slow sample, like a dye-sensitized solar cell with a larger capacitance, the sample is much slower and it behaves, or even comparing to the silicon photodiode, it is much slower and it saturates after, say, 5, 10, 15 seconds. And then if we switch light too early, it won't charge up to the value that we are interested in, and we have to increase this time window shutter opened, so we can even apply 10 or 20 seconds. So we need to increase the shutter open time. And if we turn the light off, it discharges quickly again in the case of silicon photodiode, but in this case it also discharges very slowly. And to avoid taking into account our calculations this value, we set this value, this use last not necessarily 50 seconds. We can use last 20, not seconds, percent. We can use last 20 seconds, and even we can skip last 5 or 3% to avoid this situation with unstable state just before the circuit is switching off. So, if we take into consideration this 50%, we have this value minus this value also last 50 or 20 or so on seconds, this value minus this value, and we get the point on our plot. Okay, another experiment. Let's escape experiment, and first the first up, IPC, yes, this one. So this is like a pseudo spectrum. Okay, daj mi myszkę. We measure photocurrent. We define, okay. So this experiment we perform for the whole our spectrum of LEDs. We use the first value for all, just to make sure that these measurements are performed for the same light color, the same wavelength with the same intensity. And we measure photocurrent. Here on this axis we can see the photocurrent value. It is negative because this is below, so photocurrent values are negative in our convention. And we apply potential from, in this case, for example, 100 millivolts with step of 100 millivolts up to 600 millivolts. So on this axis we apply potential with steps of 100 millivolts, and along this axis we have wavelengths. And this is a silicon photodiode. Let's switch to the presentation again. And look, our dots are not equally spaced, and this is just any silicon photodiode sensitivity curve. Silicon photodiode sensitivity maximum is in the infrared range, And if someone says that this is not so flat or not so fluent, there are some deviations from the trend, because we don't deal with equally spaced points. So this is not a real spectrum. These are just points at different values of the wavelength. And in the case of silicon photodiode, they have the silicon photodiode for different light colors, for different wavelengths, produces different current values. Let's switch back to photo GUI. And you can observe here that this point is a little bit upper than expected, but this comes from that feature that we are not exactly in the same distances between points. And if you look at potential, different potential, and you can also connect in your imagination these points, and this trend somehow reflects the 10, but this is photocurrent. Photocurrent, if we apply another axis here, and photocurrent will be increasing, decreasing, because these are negative values. So absolute value of current will increase when the light power increases. So you can see this trend on this graph. If you connect these points and these points, photocurrent as a function of potential, and for different wavelengths. We can express the same measurement result as quantum efficiency. And for this purpose, we have to, this is possible because we have done the calibration before. So if you use our cuvette, it is designed this way that we perform, if we want to know how much sample is absorbed in the sample, how much light is absorbed in the sample. So we measure, here is a window, this way, sorry. We place the calibration here, head here. This is fit to our cuvette. We make one measurement with a window, glass window, that we assume that its transparency is 100% with some error. So we measure how much sample is delivered to the, how much light is delivered to the sample. Then we can place the sample in our cuvette, which is less transparent, and we repeat the measurement of the light which is going through the sample. We can subtract these two values, and the difference is the amount of light which is absorbed in the sample. But if we say, let's assume this is absorbed. Some light may be also reflected, but then we need a integration sphere to subtract another value of the reflected light, and so on. So, having known these values, we can evaluate the light amount absorbed, more or less with some error, absorbed in our sample. And we can also, just for curiosity, look at these values. These are nearly zero. Okay, this is zero with some noise. Okay, not in this case, but usually it is a flat surface of balls. Photocurrent. So this way we produce 3D maps, so-called action maps of photocurrent or IPC versus potential versus wavelength. Another experiment, let's switch back to the presentation, is IMPS, IMVS. And until now, we have been measuring DC signals, stationary measurements. We applied one value of potential, of light. We were waiting until the circuit stabilizes. We take some measurements, we subtract some values, and we put a dot on the plot. In IMPS, IMVS, the situation is a little bit different because we illuminate the sample with a modulated light, and you remember that in dark, this is the IV curve, and if we applied more light, the IV curve shifts. When we apply modulated light, our IV curve is swinging. So these important points, when this curve is swinging up and down, we are following in IMPS short circuit current value. We are following time changes of this point, and in IMVS it is swinging, and this point is also swinging. So we register the changes, how these points follow the changes of the light. And if the changes, if we apply a low frequency, that the frequency of light, it's comparable with the time constant that depends on the capacitance of the sample, we can see that the photocurrent values reflect or just follow the changes. And the faster the light modulation is, if there are some frequencies that they are too fast, the changes are too fast to our sample, and then we observe just shifting of the phase and decreasing the amplitude. Let's switch back to PhotoGUI. And again, we don't, to PhotoGUI experiment IMPS. We go to data. So data, menu, data, load, data drugie, load data, because if we handle with a slow sample, we can handle with very slow samples with frequencies down from some milli or microhertz. So to record one full period in case of 0.1 hertz, we need 10 seconds. If we start from 0.01, then for one full period we need 100 seconds, and to respect your time, we are not going to perform a whole experiment, so we just uploaded some previous results. All results that you are measuring, you can save to file and then upload it again for study. And here you can see, this is the all results. if we start from lower frequencies on this axis and we go to the higher frequencies, we can observe that this curve flattens. And the phase, and you can observe the phase shift. This is a delay between our sample response and the incident light. We can mark any of these curves, and we can, from the slowest, here is the incident light, and here is the current value. These values are negative, and the faster the signal changes, the faster the signal changes, the delay is larger. And the amplitude is also decreasing, but in this graph it is rescaled to full screen, and only you can see on these, following these values. Okay, and we can look at components. We can look at the Nyquist graph. We can also, the Nyquist graph skips the frequency information, but we can make it on another graph, like 3D, Nyquist 3D with the frequency axis. But if you look from this perspective, it is exactly this graph. Okay, so, but first, let's get back to the presentation. There are some quantities that we should, of course, they might have been repeated in some previous lectures, and anyway, you should be familiar with them. And Alek, video, proszę. So instead of these images, we can watch the animation. This is our sample in bulk. If we apply some lights, and electron-hole pairs may get created anywhere in the sample, but if they wave functions overlap, they can recombine at the same moment, so there is no use of these carriers. But if it happens in the space charge region, they are quickly separated due to the electric field present in this part. And we have some holes that are not important for us because they are flowing away to the circuit, to the electrode. And in this layer, there are some charges that start to flow due to diffusion to the opposite electrode. Let's go. And due to diffusion, they just flow, and in a loop, let it be repeated. So the mean time that the carriers flow to the opposite electrodes is transport time. So this is that value. And some of our electrons can recombine somewhere in the bulk with holes, and this is recombination time. And let's switch back to the presentation. So instead of talking about this image, I showed you the video. And of course, we can draw a circuit that reflects some resistance of the bulk and some resistance and capacitance of the space charge region. and we record some curves, and from the Nyquist plot we click at the minimum, and 1 over minimum from IMPS. IMPS is transport time, and this is time constant of our circuit. And from IMVS plot, if we click on minimum or sometimes maximum, it is recombination time. And then from these two quantities, we get charge collection efficiency. Next, diffusion coefficient. We need to know the sample thickness, or the other way around. We can evaluate sample thickness if we know the diffusion coefficient. And after that, we can get the effective diffusion length. And let's switch to photo GUI again. After we have completed the IMPS measurement in some frequency range that we know, sometimes we have to repeat a couple of times. If we see, like, if we have a graph like this, and we see that we have to extend our range to find this minimum, or we can repeat the experiment with more points, number of samples. In this range from another one. It is hidden here. So here we define the frequency range and number of samples in this range. We can get more samples, but the experiment will be longer, will take longer. But after that, we just click at this point and another window is open. So this is the number of this point, sample number 8, frequency, X and Y components of the signal, phase and amplitude. Similarly, we can close or leave this window open, but we can open it at any time. In IMVS, we click on that point, and all these values are filled in. I know that the thickness of the sample is 10.5. No, not this keyboard. Okay, please fill in 10.5. And the rest of the values are filled in according to these equations that I've shown you before. And more or less, that's it. So I can tell you that you may be happy that you don't see all these procedures, all these efforts that our IT guys, our programmers have invested into this software. It was there were long months of hard work to make it ready, and now you just have setup and software that you just place the sample in, define some parameters, play start, wait, make 2 clicks, and you have some results filled in. Let's go back to the presentation. Good time. So maybe if you have, we can extend the coffee junction, sorry. And maybe if you have some samples of yours and you are curious how it works, how they look in our equipment, we can make it in the coffee junction. But just to summarize, so mini photoelectric spectrometer is a setup designs for which are good for students' lab for basic characterization of photosensitive samples, to make students familiar with some definitions like quantum efficiency, photocurrent, open circuit potential, and so on. And we are dealing then there with stationary parameters. We measure DC signals. And if you ever wish to upgrade it to full photoelectric spectrometer, it is possible. And if you use some of our equipment for basic characterization, we say that the hunger increases during eating. Then you may need some to get access to some more parameters, to dynamic parameters, at time constant, transport time, recombination time, and so on. And then you may ask us for IMPS, IMVS, and then you can measure these parameters in the frequency range from microhertz to up to 10 kilohertz. And just a end note, I like this quotation of Lord Kelvin, because we are scientists, we deal with science, with numbers. To be sure that we know what we are talking about, we need to measure it and express it in numbers. Then we can say that we know what is going on in our measurement and in our sample. So be aware what you are measuring, and these measurements make you on the right path to, first you have to understand the method and understand the equipment, and having that, you are on the right way to understand your sample. Thank you for your attention. And now it's time for questions or
when you buy the mini spectrometer, this LED revolver is already ready to perform the IMPS measurements. It has all the components inside.
LED revolver. Yes, now it is. Some time ago, it was an extra option that might have been ordered.
So my question is, if I buy mini spectrometer,
yes,
photoelectric spectrometer, then what I have to buy extra, additionally
license,
to have
license.
IMPS?
Yes, only the license for the software, because these are another category of products. This is much simpler, much cheaper, and to reflect all the works, all the efforts we invested to establish this setup, the software, the software to control the IMPS, IMVS experiment is much more expensive.
So I don't buy an additional controller or additional...
No, it isn't. Now it is done that everything is in the firmware software, so you don't have to worry, you just purchase another license. Because, have I said about it that, in the beginning, I said that this year we are changing the license policy, and this is a good example that when you have just a setup ready for a mini photoelectric spectrometer and you wish any other features, experiments, functionalities, you just purchase another license for another experiments.
Can you control temperature, for instance, during the experiment, and can you automatize such kind of measurements? So you let's say measure the IMPS, IMVS at several temperatures?
No, not at all. The answer is simple, no. So you have to control the temperature on your own. You have to put the setup in a stable temperature. So if you wish to extend these parameters, so it doesn't make sense to make one measurement at different temperatures because you add another parameter. So to control
Acquisition of the full IMPS IMVS spectrum, and later you change by, let's say,
Yes.
10 Celsius degrees and do the same, etc.
So this will be a custom extension, or you can make it on your own to provide stable temperature and repeat the experiment and then collect several experiments in different temperatures and then then collect the results as a function of temperature. But this is not included.
Like you have the platinum electrode in the cell. Is it possible to replace it with this graphite electrode?
Yes, I think so, because it is not. There are no settings in the software that you have to set any type of electrode. So the difference will be only in potential. So if you like to compare your results with other results with different material, electrode material, so you have to shift, or there is different reference, so it's up to you. If you perform all your experiments with your own electrode, so you compare your results to other results with the same electrode. But if you want to compare to other results, so you have to be aware that there is any potential shift, yeah?
I have a question in relation to the question of Dr. Kuncewicz about this applicability of revolver and potentiostat that was originally purchased just for simple DC voltammetry and this, let's say, mini photoelectric spectrometer application. Are these new revolvers capable of doing this higher frequency modulation, or the older ones, let's say, purchased 1-2 years ago, are also capable of this? I'm asking because I tried to do this using the software for mini photoelectric spectrometer and just inputting the modulation time like much less than seconds to control it in several hertz frequency, but it seemed to losing some steps, like the diode was not quick enough, switch on, switch off.
I guess you already have such a setup, yeah?
Okay. I mean,
you already have such a setup and you are thinking about the upgrade?
Yes.
Okay, so I'm not sure when the change was applied, so we can check it if you are interested. So we can check it for you and tell you which version you have and what to be extra purchased to.
So I have a question, so maybe a comment, but you wanted to make it switching off and on?
Yes.
But this modulation is not that case. It's not on and off, it's just you have a sine or cosine function of the light intensity. It's something different. So you cannot do it just by switching on and off the light. Okay, so, and my question is, according to the system, is it possible right now, because we have one of the first maybe IMPS version, measurement of the light intensity during the measurement, during the, yeah, because
okay, similarly as in the photoelectric spectrometer, you mean?
yes.
In this case, we don't have to measure it because the light is delivered from LED and we control the power electrically. So we.
But if temperature is changing during the time, it will change the light.
We assume that the temperature is stable, and it is up to you in your lab. If you open window during the experiment and the temperature is unstable, so this is your fault, let's say.
I was wondering, you said that you use the calibrator as a sample, but for that you need to connect the cables, right? The calibrator to those crocodiles. How do you connect it?
Crocodiles.
To get the readings of the current and stuff, you need to connect it with the cables, not with that
Okay.
line.
You can see there is another feed through. We connect the calibrator to the. Okay.
Yes, that's what I'm asking, but how to connect it? Which one?
Just take reference
Look.
and
What you mean?
Yeah, but now you get just the reading from the light, not the current and stuff. If you have connected to...
This is the calibrator. This is the calibrator head. We place it in. We have another feed through BNC, so we can connect we can place this calibration head exactly in the spot where the sample is, and we can read the value of the light which is reaching the sample.
Yes,
and then we know.
Reading the current.
I can tell. Can I?
If we repeat then experiment, we know the value of light, and all other parameters are the same. We don't change anything. And if we place the sample in the same spot and connect sample to the...
I understand that, but you said at the beginning that you use the diode as a sample.
As a sample. Okay, so we connect it to different... Yeah, so... Okay.
Yeah, that's what I'm asking.
Okay. Another cable, and to BNC.
So there is another cable inside.
Yes.
I don't have that.
And to this cable, the red working electrode, here it is explained.
I see.
So
Okay.
I connect working electrode to the outer terminal, and in the middle, blue and black electrodes.
Okay. Thank you.
You're welcome.
I have maybe a naive question compared to others, but which function do you use to modulate the light? Any specific function?
Just a sign. This the easiest, and with only one harmonics. Yeah, but this is good question. Oh, thank you for that question, because the conference is about nonlinearity, and the sample is nonlinear. And if we look, if we swing the light, if we are swinging here, and the signal goes over a nonlinear path on this piece of curve, then we may expect that the output signal, if we just modulate with a single sign, will be distorted, right? And this is another tool. Let's go to Photo GUI, Alek, please. We have to go to IMPS, IMVS. And for these results, we can look into harmonics, higher harmonics. So this is the first harmonics, and the more of higher harmonics you see here, the more nonlinear is your sample. Another tool for higher harmonics observation. Thank you for that question.
what's the lifetime of the diodes?
Oh.
It depends on the diodes.
Yes.
Thousands of hours.
You know, in books,
Just
in books.
the range, not
Uh,
exactly, but.
Okay, you
Because
can.
when
yeah.
we made some measurements with diodes, we have some problems with przepalenie.
Okay. Yes, the intensity decreases over some time.
Yes.
So you can perform the calibration again after a year and you see the difference and use new calibration to be sure that you know the light value. But in books, they say they write in books that I guess in ideal case it is 10 to 5, so it is over 100 years, but 10 to 5 hours, it's, I guess, 111 years. I may be wrong, but it was when I was in a high school, so at school about electronics, about LEDs, so theoretically their lifetime is that range, but of course it means that after some hours its light intensity decreases by half. And of course, in real world, they decrease faster, but during an experiment, we assume it is stable because you are not able to observe these changes anyway. And after a few months, you can repeat the calibration to make sure about the values.
Okay, thank you.
You're welcome. Okay. I see you're fed up with information, and now it's time to get fed up if someone's breakfast was not enough. There are some or are not. Thank you once again for your attention.